Namaste everyone.
Namaste, sir.
Namaste, sir.
Namaste, sir.
Namaste, sir.
Namaste everyone. And all of you, please rename yourself. I mean, whatever name is present on your screen, just change it. Okay. Rename yourself, everyone. Okay. So last class, we started with this particular chapter. We saw some basics. We understood the laws of reflection. And we did some questions. Okay, towards the end. In today's class, we are going to discuss spherical mirrors. So today's lecture is going to be the most important one in this particular chapter, entire chapter. See, I will take few more lectures. I will take actually 7 lectures, around 7 lectures. I will take 6 to 7 lectures. This is the most important lecture. Okay. If you get it, the chapter will become very easy. Okay. So please listen with focus. Okay. Don't actually be distracted. And have your video switched on, everybody. I will not be repeating this every time. Suvarshita, what is the time right now? Suvarshita? I'm not able to hear you actually. Maybe there's some issue. I'm not able to hear you. What is the time right now? Please, everyone, my humble request, be before time. Okay. Don't join late. It will not be helpful at all. Okay. Perfect. So I told you we are going to discuss spherical mirrors in today's class. Now, what is spherical mirrors? So a spherical mirror is that mirror whose reflecting surface is a part of a hollow sphere of glass. So here you have a hollow sphere of glass, right? Yes, inside it's hollow. Okay. I have taken a jar. Okay. I have not, see, this is not it is not a sphere. It is not a sphere actually because top is empty, right? So, I mean, you don't actually bother about that. You think it is a hollow, you think it is a hollow sphere. See, sphere means it will be like a tennis ball. Okay. You can think of a tennis ball. That is actually a sphere, tennis ball. Inside it will be hollow, right? Tennis ball. So, but this is actually made up of glass. Tennis ball is not made up of glass, right? So, what is a spherical mirror? A spherical mirror is that mirror whose reflecting surface is a part. It is only a part. It is only a part of what? Of hollow sphere of glass. Okay, so we are having a hollow sphere of glass. You can just imagine that this is a hollow sphere made up of glass. You can imagine that this is a hollow sphere. This is a hollow sphere made up of glass. Okay. Now, if I want to get spherical mirrors, what I can do is I can cut this hollow sphere using a cutter, sharp cutter. I'll take a sharp cutter. I will take a sharp cutter. Okay. You just imagine that I'm having a sharp cutter and I'm going to cut maybe a small part from here. Okay. See, when I cut, you'll actually get this part out. Okay. This part will come out. Okay. So you'll get something like this. You'll get something like this. I repeat, we are having a hollow sphere of glass. We are taking a sharp cutter. Using a sharp cutter, we are going to cut from one of the sides. Maybe actually from here, we are going to cut. So you'll get something like this. Okay. This is not actually glass. I mean, this is steel. But you just imagine that this is glass. You just imagine. This is made up of glass. So glass will be transparent, right? So you imagine that this is also transparent. You imagine. This is transparent. You imagine. Okay. You can look through it. Okay. So I have a hollow sphere of glass. From that, I'm going to cut a part of it using a sharp cutter. See, when I cut, okay, in 2D, how will I represent? See, in 3D, I cannot actually draw it properly. So I'll just use 2D. Okay, this part will come out, right? See, this part will come out, right? This part will come out. This part will come out, right? So I'll actually draw it here. Okay, something like this will come out. Okay, this part, no, this part will actually come out. When you cut using a sap cutter, no, this part will come out. Now, if you extend this part, no, see, if you extend this part, okay, just 1 minute. Okay, see, if you extend this particular part, okay, if you extend it, or maybe I'll show it here itself. If you extend this particular part, right, you imagine there is only a blue color, only this part is there. Now, if you extend this, right, if you extend this like this, you will get the actual sphere. Okay, if you are just having the part, if you are just having a part of the sphere, hollow sphere, and if you extend that, no, if you extend that, you will get back the sphere. If you are having a part of the sphere and if you extend that, you will get back the sphere. Yes. Now, when we are cutting a part, that is actually this one, when we are cutting a part of this sphere, I will get something like this. In 3D, I'll get something like this. In 2D, we'll get something like this. In 2D, only this much part will be there. Okay, that is 2D. Okay, but actually, you'll get something like this. Now, this is transparent, right? I mean, I can see through it. Okay, this is transparent. This is made up of glass, right? So it is transparent. Now, last class we have seen how do we make plane mirrors. Last class we have seen how do we make plane mirrors. So we take a glass slab, we apply silver coating on one side. To protect the silver coating, we apply some red paint or whatever gray paint. And if you look from one side, it will become reflecting. The other side will become non-reflecting. So what do we do? In 2D, we just draw a straight line and non-reflecting surface will mark by hatch lines. So in a plane mirror, one side will become reflecting, another side will become non-reflecting. So non-reflecting will mark by hatch lines. Yes or no, everyone? This is what we saw last class. Perfect. Now I'm having a sphere. Actually, I'm having a part of a sphere. That is this one. I have taken a hollow sphere of glass. Okay. And from that, I have taken a hollow sphere of glass. And from that, I've actually cut a small part. Okay. I've cut a small part. And that small part is this. Now I'm going to make a spherical mirror. Now, the type of spherical mirror which I get depend on the surface which I'm actually painting or the surface which is reflecting. So there are two types of spherical mirrors, concave and convex. Okay, there are two types of spherical mirrors, concave and convex, and it depends on where the reflecting surface is. Okay, we'll just focus on the reflecting surface. Okay, so I'm having a small part of the hollow sphere. Yes, this is a small part of hollow sphere. I'm going to apply silver coating outside. I'm going to apply silver coating outside. Yes. Now silver coating can undergo a lot of scratches. So to protect that, I'm going to apply some paint, red paint or gray paint, whatever you want, you can apply. So this surface will become non-reflecting. We are not bothered about non-reflecting. We are bothered about reflecting. Inside it will be reflecting. Okay. Inside part it will be reflecting. Why? Because outside we applied the silver coating. And to protect that, we applied some paint. So outside obviously it will be non-reflecting. Inside it will be reflecting. When the reflecting surface is curved inwards, concave. It's like a cave, right? It's inside. We can go cave, concave. When the reflecting surface is curved inwards, it is called as a concave mirror. Are you all getting yes or no? It's a concave mirror. Okay, so actually I had a hollow sphere of glass. From that I cut a small part. I got something like this. I applied silver coating outside, and to protect that, I applied some red paint. So inside became reflecting. When the reflecting surface is curved inwards, reflecting is inwards, it is called as a concave mirror. Now, how will I represent in 2D? So in 2D, I will actually just draw this blue line. Okay, this blue curve. Okay, just blue curve, and I'll mark the non-reflecting surface by hatch lines. Okay, see, all this is not required. I'm just showing that this blue part is a part of the sphere. That is why I've extended that. This blue part, this spherical, that is the only reason it's called spherical mirrors, because it is a part of a hollow sphere of glass. Okay, so I'm extending that to show you that it is a part of a sphere. Yes or no, everyone? Yes, perfect. Now, so this is what? Concave mirror. So this is actually what? Concave mirror. Concave mirror. So when the reflecting surface is curved inwards, it is called as a concave mirror. Now, actually, when I cut, now I got something like this, right? When I cut from the right side, I got something like this, right? I could have also applied silver coating inside. I could have also applied silver coating inside and the red paint inside. Okay, I could have done that. So in that particular case, outside will become like reflecting. I can apply silver coating inside, and to protect the silver coating, I can apply some red paint inside. So outside will become reflecting. When the reflecting surface is bulging out, when the reflecting surface is bulging out, it is referred to as a convex mirror. Okay, when the reflecting surface, just 1 minute. Somebody, actually some students' power went off. Just 1 minute, hold on. Arrange perfect.
Yes, sir.
You are able to see my screen?
Yes, sir.
Power went off, right?
Yes, sir.
Okay. Okay. So when the reflecting surface is bulging out, okay, when the reflecting surface is bulging out, it is referred to as a convex mirror, convex mirror. And one more thing, I have already told you, I have a screen on my right side where I'm looking at each and every one of you. Please, everyone, don't actually force me to ask you to switch on the video every time. As soon as the class starts, throughout the class, throughout the session, keep the video switched on. Think that I am teaching directly, because you cannot see anybody's face. You can see only me. You can see names, okay? You can see the names of other students, but you cannot see their faces, okay? So think that I'm teaching you alone. Think like that. If you have some doubt, feel free to ask. Okay, don't even bother about anybody. Think that you have only come to learn from me. That's it. You think like that. Okay. Okay. Soumil will come to that. Okay. So now we have learned that, I mean, if I'm applying the silver coating outside, and to see, silver coating can undergo scratches, so we have to protect that for sure. So I'll apply some paint over that. So inside reflecting means it is concave. If outside is reflecting, when will outside become reflecting? When we apply the silver coating inside and the red paint inside, we can get the reflecting surface outside, or it is bulging out. That is convex mirror. Now I can actually also make a cut from this side. See, I can make cut from any side. That is totally up to me. Concave or convex depends on where the reflecting surface is. That's it. If reflecting surface is inside, it is concave. If reflecting surface is outside, it is convex. So simple. Yes or no, everyone? Yes. Now see, I could actually make a cut from here also. Okay. Suppose I take a cutter. Maybe I'll take a cutter, and maybe I'll actually cut like from here. Okay, something like this. Okay. I'll make a cut, something like, wait a bit. I'll actually use straight lines only. It'll be easy. I'll make a cut like this. Okay. So I'll actually get something like this, right? I'll get something like this, right? I'll get a curved part, right? I'll get a curved part. So that curved part, what I'm going to do is, I'm going to apply silver coating inside and then red paint. So inside will become non-reflecting. Inside will become non-reflecting. Outside will become reflecting. So this is what? Convex. Convex. Convex mirror. Even convex mirror, no, it is a part of that hollow sphere. See, it is only a part, no. See, whatever mirror we have taken, it is only small, only this much part, no. It is only this much part. It is only this much part. That's all. It is only this much part of the hollow sphere. So that means if you extend this, okay, if you extend this, okay, you will get back this sphere. Yes or no, everyone? Yes or no, everyone? Yes. Sanskriti. And one more thing, everyone. I mean, see, just 1 minute. I'll just show you. Okay, so this is a question. Sir, is sharing me an example of concave mirror. See, I have not yet come to the application. So I request everyone, actually, first of all, listen with patience. Okay. I'm going to discuss each and everything in detail. Okay. So have patience first, everyone. If you have some doubt which is coming up in your mind, maybe you can make a note of it in your notebook. Okay, instead of typing, right? you can just make a note. It's for everyone, not only Sanskriti, it's for everyone I'm telling, okay? You can all just make a note of it in your notebook and just see whether it is getting clarified during the class. If not, I'll ask you, have you all understood? That time you can ask. Otherwise, obviously at the end of the class also I'll be waiting. You can ask your doubts that time for sure. Okay. Suraj, what is the time right now?
Sir, 6:50, sir.
What time you joined?
Sir, I have joined 6:45, sir.
Why?
Sir, I told you, sir, I was having issue with my tab, sir. That's why.
All of you, my humble request, try to fix all your issues like internet issues, tab issue, laptop issue. All this will come only before the class. Okay. So please make sure that you fix it before it, like long before the class starts. Okay. So that you are not struggling. Okay. At the end. Okay. Perfect. So yeah. See, we are going to see, we have actually applications of spherical mirrors. In like we have some applications, we'll discuss that. Okay. I'll discuss all these things. Okay. So yeah, just everyone just listen first. Okay. So now both concave mirror and convex mirror, they are actually part of the hollow sphere of glass. Okay. Here basically a reflecting surface is inside. This is what? A reflecting surface. Okay. Here reflecting surface is bulging out. We say bulging out. Okay. Or curved outwards. Okay. So this is actually reflecting. I'll give you all the definition. Please don't write anything actually right now. You just listen, everyone. Okay. Now, I told you that whether it is concave or convex, both are part of a hollow sphere of glass. So if I take this small part and when I take this small part, when I extend, I'll get this sphere, right? Now that sphere will have a center, right? Maybe here it will not be a perfect place. I will actually do it in the next page. Okay. Maybe I'll delete this also. Okay, you have understood that suppose if I have a concave mirror, okay, if I have a concave mirror, I'll just take it like this. Okay, actually concave or convex depends on where the reflecting surface is. Okay, suppose I have a concave mirror. Okay, reflecting surface is inside, right? So that is concave. I'll extend this to get the sphere. Maybe I'll draw a bit bigger, okay, because I want to write a lot of things here. Okay, I'll make it a bit bigger. Okay, I want to write a lot of things here. Okay, just 1 minute. Okay, I don't have a curve part. Okay, this is looking good. Okay, so I mean, this is the non-reflecting surface. So always hatch lines we have to use for non-reflecting surface. Okay. See, I'm not using compass, so I mean, it will not be very curvy. Okay. So you have to ignore whatever, like some like irregularities and all you have to ignore. Okay. So if you extend this, right? If you extend this, you will get the sphere. Okay. It's not perfect, but it's okay. See, just for understanding, I have drawn this. Okay. So now this sphere will have a center, right? See, I took a spherical mirror. Spherical mirrors are part of a hollow sphere of glass. When I extend the spherical mirrors, I'll get a when I extend the spherical mirror, I'll get a sphere. That sphere will have a center, right? That center is called a center of curvature. Okay, I'll give the definition. Center of curvature. All of you, first of all, listen. Center of curvature is the center of the sphere of which spherical mirror is a part. Because spherical mirror is a part of a sphere, like of the spherical hollow sphere of glass, right? Spherical mirror is a part of hollow sphere of glass, right? So how do we define center of curvature? Center of curvature is the center of the sphere of which mirror is a part. Mirror is a part. Okay, it's only a part. Okay. So what is C? C is the center of curvature. Center of curvature. Okay. Now, if you take this, see, mirror is only this much part, right? See, mirror is only, see, reflecting surface is inside actually. Okay, reflecting surface is inside. See, mirror is only this much part, right? Let's see, other things I have extended just to show that it's part of a sphere. Mirror is only this much part, right? Now, when you take center of this much part, right? See, yellow part is only the mirror. So when you take center of that, no? When you take center of the yellow part, center means middle. See, from here to here, it will be of some distance, right? When you take center of that, suppose it comes here. Suppose it comes here. That is called as pole. What is pole? Pole is nothing but the center of the reflecting surface. Mirror is a reflecting surface, right? Center of the reflecting surface is called pole. What is that called? Pole. We use capital P for that. What is pole? Pole is the center of the reflecting surface or the mirror. Okay. Yes or no, everyone? Are you all getting? Yes or no? Perfect. 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 Now, an imaginary line passing through the center of curvature and pole. And imaginary, see, generally imaginary line will draw by dotted lines, but here we'll use only straight lines. Okay. In the ray diagram, so I'm going to use only straight lines. So an imaginary line which is passing through center of curvature and the pole is called as the principal axis. Okay. So a straight line or imaginary straight line. See, it's not perfect. I mean, still I have got it. Please ignore. I mean, it should exactly pass through these 2 points. Okay. This green line, no, this should exactly pass through these 2 points. Okay. An imaginary straight line passing through the center of curvature and the pole is called what? Principal axis. Principal axis. Okay. Now you look at the sphere. This is the sphere. Sorry. This is the sphere. This is the center of the sphere. So from center to here, this is radius of the sphere. Yes or no? Yes. So that distance, the green one, that is called as radius of curvature. What is that called as? Radius of curvature. From here to here, no. We call radius of curvature. How do you define that? I'll give you the definition. Don't write. First listen. Understand. Radius of curvature is the radius of the sphere of which mirror is a part. You always have to mention that mirror is a part. If you don't mention, they will not get full marks. Okay. Radius of curvature is the radius of the sphere of which mirror is a part, because spherical mirrors are part of a hollow sphere of glass. Okay. I'll give the definition. Don't worry. Just 1 minute. Okay. Sorry. Okay. So the distance from here to here. Okay. Maybe I'll actually show it like this way. This is what? A radius of curvature. And we use capital R for that. Okay. We use capital R for that. Radius of curvature. Okay. See inside, see this is a concave mirror because inside it is reflecting. Yes, that I don't have to write again. I have already written. You can understand now wherever hatch lines is, that is non-reflecting. Yes or no, everyone? Yes. Now see, same way, if I have convex mirror, see this is concave. Suppose if I have convex, look here. So this, if this is a convex mirror, see convex mirror reflecting surface is outside. Okay. Convex mirror reflecting surface is outside. So that will also have a center. Yes or no? Center of the reflecting surface is called pole. Yes or no? That is called pole. Yes or no? When you extend the mirror, you will actually get a sphere. That sphere will have a center. That is called a center of curvature. Center of curvature is the center of the sphere of which the mirror is a part. And imagine a straight line passing through the center of curvature and the pole, that is called principal axis. So here also you'll have all the things. Yes or no? Perfect. 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 Okay. And all of you all of you please try to be, I mean, I'll just show you what I want actually, everyone. Just 1 minute. Okay. See, I should be able to see you like in this screen. Okay, some people know actually your camera is on, but you are actually here. I mean, I can just see only a small part. Okay, you should be exactly in between. Please remember, everyone. Okay, you should be exactly in between. You have to like put yourself in exactly in between. Okay, most of you have done, but there are some like people who actually, I mean, they have turned on the video, but there is no point. I mean, they are actually somewhere outside. I'm not able to see their face itself. Okay, don't do like that. Okay, yes. And all of you just listen. You don't be busy. I mean, don't think that I'm not getting chance to write. Everything will be shared. You just have to write after the class is over. That's all. Okay. So you have understood what is like pole, what is center of curvature, what is radius of curvature and all, right? So here actually I have taken, this is actually what is concave mirror. I have given the definition. A spherical mirror whose reflecting surface is curved inwards, that is faces towards center of the sphere, is called concave mirror. Clear everyone? Definition? Diagram also very clear? Perfect. Next. Next. A spherical mirror whose reflecting surface is curved outward is actually called a convex mirror. It's curved outward. It is outward. That is why you forget about this F. I'll tell you what is F also. I have talked about C. I have talked about P. What is P? Can you all put in the chat box? What is P? Can you all put in the chat box? Definition of P. I want definition of P. Okay. I want the definition of P. P is pole. What is pole? Okay. What is that pole? Define. It will not take much time. Okay. Everyone can define. Wow. Aisha, very nice. Naitik, good. Very good, Naitik. Very nice. Yes, Amrita, very good. Yes, Sanskriti, very good. Yes, Janav. Yes, Meenal. Yes, Aryan. Very good. All of center. Okay. Convex center of the convex. Okay, we can say like that also. Okay, perfect. See, it is basically the center of the reflecting surface. Reflecting surface is nothing but a mirror. Okay. So here is a convex mirror. So some people actually have said like it is the center of the convex mirror. That is pole. Okay. If it is so we don't have to actually mention that concave or convex. We just have to mention center of the reflecting surface or mirror, whatever. Okay. Next, moving forward. Okay, here actually there is a diagram which is actually very easy for you to understand a lot of things. What is pole? See, here we have a concave mirror because reflecting surface is curved inward. Here we have a convex mirror because reflecting surface is bulging out. Pole is the center of the reflecting surface. See, this is a reflecting surface. That this is pole. Okay, center of curvature is this one. Okay, it's a concave mirror they have marked. Radius of curvature means from here to pole. Okay, okay. And see, this is a hollow sphere of glass. Correct. This is the principal axis, and imagine a straight line passing through the center of curvature and the pole. And for convex, they have actually again given the diagram. Okay, you can all draw this diagram also in the notebook while actually writing class notes. Okay, okay. Next, moving forward. Okay, see here I have given some more definitions. Okay, the center of the reflecting surface of a spherical mirror is a point called the pole. You write this in the exam. I mean, you learn it, you write in notebook also. The center of the reflecting surface of a spherical mirror is a point called the pole. It lies on the surface of the mirror. Okay, pole is lying on the surface of the mirror. Okay, the pole is usually represented. I mean, you don't have to write all these things. I mean, this is enough for the definition of pole. Okay, the pole is usually represented by the letter P, capital P. Okay, the center of the sphere of which the reflecting surface of a spherical mirror forms a part is called as center of curvature of the mirror. It is represented by capital letter C. The radius of the sphere of which the reflecting surface of a spherical mirror forms a part is called as radius of curvature of the mirror. It is represented by capital R. So from here to here, no, that is capital R. An imaginary straight line passing through the pole and the center of curvature of a spherical mirror is called principal axis. All definitions clear, everyone? Perfect. 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 Next, moving forward. Okay. We are going to discuss principal focus or just focus. See, wherever the word focus is mentioned in our syllabus, it is always principal focus. Okay, especially in mirrors. Okay, it is principal focus. Focus means principal focus. Now, what is principal focus? Okay, See, to get the principal focus of any mirror or even lens, okay, remember, whenever we want to get principal focus, we'll pass the rays parallel to the principal axis. See, principal axis is this line. Principal axis is this line, okay? Line to the center of curvature and pole is that is principal axis. To get the principal focus of a mirror, any mirror, we are going to pass the rays parallel to the principal axis. If you look, we have number of rays. All these rays are parallel to this principal axis. All these rays, okay? All these rays are parallel to the principal axis. I will just take one ray to make you understand the concept of reflection, okay? And other, like, I mean, you can draw the other rays by yourself automatically. It's very easy, okay? So I'll just take one ray. Suppose a ray is coming parallel to the principal axis, okay? A ray is coming parallel to the principal axis. Okay, this is a ray, right? Ray is the path of light. Yes. Now the ray of light is going to strike the mirror at a point, right? This is the point. What is this point called as in the chat box, everyone? The ray of light which is coming will strike the mirror at that point, right? What is that point called as? Wherever light strikes the reflecting surface, what is that point called as? Whenever light is coming, it will strike the mirror at a point. What is that point called as? No, Naitik, no. Yes, Aisha, very nice. It's actually the point of incidence. Okay, the point of incidence. Okay, when a ray of light is coming, it is going to strike the mirror at a point. That is called as point of incidence. Okay, so this is point of incidence. Yes or no, everyone? Yes or no, everyone? Perfect. All of you, please focus. I mean, don't think of anything. You just listen with an open mind. Trust me, you'll be able to understand each and everything taught here. Okay. If you have the mindset that I only want one-to-one class, then obviously you cannot understand anything here. Okay. Please listen with an open mind. Just listen with an open mind. Okay. You'll understand each and everything taught here. Everything you'll understand. Okay. This is called point of incidence. We have learned in the previous class that we draw the normal at the point of incidence and to the reflecting surface. We have learned last class that we draw normal at the point of incidence and to the reflecting surface. Yes or no, everyone? Yes. And last class we learned another concept that radius is perpendicular to the tangent at the point of contact. Yes or no, everyone? Radius is perpendicular to the tangent at the point of contact. Now, see this, see, just 1 minute. This mirror is a part of a sphere. So I can actually extend. See, if you take 2D of a sphere, it's actually a circle, basically. Okay. So, see, it's not perfect, okay, but it's okay. You just understand the concept, okay? Don't actually focus on the like small parts, okay? See, if you just focus on this part, it looks like a circle. Although it is a sphere, but 2D it's a circle, right? Yes, 2D is a circle. Now, circle is a collection of infinite points. Circle is a collection of infinite points. Now, this is just one of the points. This is just one of the points. At that point, I can draw a tangent. Yes or no? At that point, I can draw a tangent. Let me draw a tangent. It's not a perfect tangent. Okay, but just imagine this is a tangent. Okay. At that point, I can draw a tangent. What is tangent? Tangent is a line which touches the circle at exactly one point. Exactly one. It is touching the circle at exact. It's not a circle, it's a sphere, but I'm taking, see, 2D of a sphere is a circle. Okay. So this is actually the tangent. The blue color is the tangent. Okay. And this is the point of contact. See, this is the point of incidence is the point of contact, right? See, wherever tangent touches a circle, no, that is called as point of contact. Okay. Now, we have learned last class that in the case of a circle, radius is perpendicular to the tangent at the point of contact. Now, if this is the center of the circle, if this is center, it looks a bit odd. I mean, see, circle, I mean, I should have drawn a bit big. Okay, this is not a perfect circle, but you just see, ignore all those things. Okay, if this is the center of the circle, okay, if I join this line, okay, this is radius. Yes or no, everyone? Yes. Now, this yellow color, maybe I'll change the color. This is the radius. From here to here will be the radius. Why? Because center and any point on the circle, if you join from center to any point of the circle, it is radius. So this is radius. And radius is perpendicular to the tangent. Radius is perpendicular to the tangent at the point of contact. Radius is perpendicular to the tangent at the point of contact. Yes. That means what? In the case of spherical mirrors, a line passing through C is going to act like a normal. Is that clear, everyone? I repeat. Okay. If you take this as a circle, this is the center of a circle. From center to any point you join on the circle, it is radius. Yes. Last class we have learned that a radius is perpendicular to the tangent at the point of contact. So this will be perpendicular. And normal, where do we draw normal? At the point of contact. At the point of contact, we draw normal, and to the reflecting surface. See, this is a reflecting surface, right? See, here reflecting surface is curved actually. Reflecting surface is curved. So we draw normal at the point of contact and to the reflecting surface. So normal in the case of spherical mirrors, no, will always pass through C. You please remember this. Why it will pass through C? Because see, radius means from center to here, right? So if you extend, it will always pass through C only, right? Yes or no, everyone? Yes. Now normal we always draw by dotted lines. Normal we always draw by dotted lines. Dotted lines. That means my normal will be something like this. Please use scale and pencil while drawing at home, okay? So this is normal. Yes. Now, this is normal. What is this? Incident ray. The ray which is coming is incident ray, right? So what will be this? Angle of incidence. Yes or no, everyone? Yes. Now, as per the laws of reflection, I is equal to R. Correct? So we can actually take our protractor and actually we can actually, whatever is I, same R will mark, and we can draw the reflected ray. Actually, you will find that the reflected ray, no, will pass through F. You will find out, okay? It will pass through F. Okay, so this is the angle of, this is actually the angle of reflection. Okay. So are you all able to understand how the reflection takes place in the case of a spherical mirror? And here also the laws of reflection are applicable. Yes or no, everyone? Yes or no, everyone? Perfect. 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 Okay. So now, and all of you, please don't actually, don't actually keep typing. Okay, the same thing. Okay. Perfect. Okay. So now I have just taken one incident ray, right? I have taken one. But if I take many also, the same laws of reflection. See, if you take this also, again, point of incidence, I can draw normal. See, all of you focus, please focus, okay? This is the incident ray. This is the point of incidence. I can draw normal. Normal will always pass through C. Angle of incidence, angle of reflection. So reflected ray will actually pass like this, okay? So when the number of rays are coming parallel to the principal axis, all the rays are parallel. See, they are parallel to the principal axis. It has been found experimentally. It has been found experimentally that when the number of rays are coming parallel to the principal axis, after reflection, all the rays will pass through one point. That point is called as focus. After reflection, no, all the rays will actually pass through only one point. That is actually principal focus or focus. Okay. Now there is one more condition attached to this, which I'll tell you later on. But as of now, just remember that whenever rays of light are coming parallel to the principal axis, after reflection from the mirror, they will actually pass through a point that is called principal focus or focus. So principal focus of a concave mirror is a point on its principal axis. See, this is a principal axis. This is the principal axis. Principal focus of a concave mirror is a, sometimes they're asking this type of questions. Define principal focus of a concave mirror. Okay. So we have to actually use that word also, and definition will change a bit. Like when it is convex, definition is a bit different. Okay. So principal focus of a concave mirror is a point on its principal axis to which all the light rays, which are parallel and close to the axis, converge after reflection from the concave mirror. Just 1 minute. Okay. So the principal focus of a concave mirror is a point on its principal axis to which all the light rays, which are parallel and close to the axis, converge after reflection on the concave mirror. Okay. And the distance between the pole and the focus is called as what? Focal length. The distance between the pole and the focus is called as what? Focal length. And focal length we use only small f. Focus we use capital F. Focal length we use small f. Okay. Are you all getting or not getting? Yes or no? Perfect. 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 Let's move forward. Let's move forward. Next, we have principal focus of a convex mirror. Convex mirror means what? It is the reflecting surface is bulging out, correct? So now, here there is actually a bit of a difference. Actually, here we'll actually get the principal focus on the other side. If you look at concave mirror, right? The principal focus is left side. Okay. Now, if you look carefully, when the number of rays are coming parallel to the principal axis, after reflection, no, they're all converging. After reflection, they're all converging at one point. That is why concave mirror is also called as a converging mirror. In the numericals, sometimes they will not use the word concave mirror, they will use converging mirror. So concave mirror is also called as a converging mirror because it converges. Okay, it brings all the rays of light at one point after reflection. It's a converging mirror as well. Okay. Now, if you take a convex mirror, no, I'll take one ray, just one ray to explain. Okay, suppose I take a convex mirror and a ray is coming parallel to the principal axis. Okay, I take a ray and the ray is coming parallel to the principal axis. What is this point called as in the chat box, everyone? What is that point called as? Yes, Meenal, we have to mention all those points. I mean, whatever I said, right? I mean, we have to write everything. If it is concave, we have to define that like that way. If it's convex, we'll define this way. If they don't ask concave or convex, we can actually define for any one mirror, and that's all. It's point, this is point of incidence. Perfect. This is point of incidence. Perfect. Now, concave or convex mirror, both are part of a hollow sphere of like glass. That means if I extend this, just 1 minute. All of you just give me 2 minutes, okay? Just give me 2 minutes. We'll just, you try to recall whatever we have learned. Just Okay, sorry. Okay. Yeah. So now, when I have a convex mirror, when a ray is coming parallel to the principal axis, this is point of incidence. At the point of incidence, we draw the normal and to the reflecting surface. See, reflecting surface is actually bulging out. So at this point, we'll draw the normal. Correct? Now, see, if you extend this, you'll get the sphere. Yes. And this is the center of the sphere. Just assume it's a circle. Okay. It's a circle. In a circle, radius is perpendicular to the tangent at the point of contact. Now, I can assume this is a point on the circle. I can draw tangent at that point also. I'm sorry, actually, I'll use that line because it's very difficult. Okay. I'll actually draw like this. Yes, this is a tangent, correct? Now, you don't have to draw all these things, okay? You don't have to draw tangent and all. Actually, this is only for understanding. I'm drawing all this, okay? It's not required, actually. Okay. So at that point, I can draw tangent. And we know that radius is perpendicular to the tangent at the point of contact. Yes, that means if I join this point to this one, this center, right? Yes, if I join, this is radius, and radius is perpendicular to the tangent at the point of contact. Yes. So normal here will be a line. Just 1 minute. Okay. I don't know why it is happening. Okay. So normal here will be, see, normal we have to use only dotted lines. Okay. So normal will be a line through this, through C. Yes. Now, actually, you also have to extend this. Okay. So you take your scale, I mean, keep extending. Okay. You have to extend this side also. Why we have to extend this side? Because here, this is the incident ray, right? So normal has to be extended because normal cannot be only this side. We have to extend also, right? Then only we'll get angle of incidence. Okay. Now, actually, in the case of a convex mirror, no, after reflection, the ray will not converge, they will diverge. Okay. Maybe I'll take another ray to be able to explain. Okay. Suppose I have another ray which is actually coming. So this is point of incidence. Yes. This is point of incidence. Don't draw this much dot, this much big dot for point of incidence. Just a small, it's a small dot. It's a fine dot, fine. Okay. So now, when you join this to this is normal, correct? Because it is radius. Radius is perpendicular to the tangent at the point of contact. Actually, I can draw tangent here. I can draw tangent here, and that this radius will be perpendicular. So this is the normal. So what is the angle of incidence? This is the angle of incidence. Angle of incidence is the angle between the incident ray and the normal. Yes. Now, whatever is I, the same will be R. I is equal to R as per laws of reflection. Okay. Now, it has been found experimentally that the reflected ray, this is the incident ray, the reflected ray appears to diverge from the focus. I repeat, in the case of a convex mirror, the reflected ray appears to diverge from focus. I repeat, the reflected ray appears to diverge from focus. Okay. Now, what many students will do is, they will actually draw the, I mean, whatever is the angle of incidence, like they will try to actually measure it approximately, and they will draw the reflected ray. They will draw the reflected ray because it is going to diverge only. It is not going to converge, it's going to diverge. They will draw the reflected ray here, and they will draw the reflected ray here also. This is what many students will do. Okay. They will use scale and pencil, and they will draw the reflected ray here also. This is R. This is actually R. Okay. Now what they will do randomly, they will actually just join this to this and this to this. Okay. They will join like this. This is the way they will do. Now, light always travels in a straight line. See, if this is a reflected ray, I mean, even if you trace backward, it should be a straight line. Yes. Now this is not appearing so, right? See, this is a reflected ray. Now this is appearing a bit bent. Backward, it is bit bent. Yes or no, everyone? Yes. So what I teach my students to do is, See, this is not correct procedure. I mean, you should not draw the reflected ray first. In the case of a convex mirror alone, don't draw the reflected ray first. Don't do it. What you do is, you join the point of incidence. You join the point of incidence to focus using your scale. You join the point of incidence to the focus using a scale, using dotted lines, okay? Why dotted lines? Because it is actually, see, actual rays will use straight lines. It is not, I mean, it is not actually coming from there, right? It is appearing to come from there. Okay, so that is why we use dotted lines. Okay, other side we'll use dotted lines. Okay, in the case of a convex mirror. Now I'm going to join the point of incidence to focus. Now take a scale and put the scale on this line. Some part of the scale will be here. I will take a scale. I'll put a scale on this line. Okay, I'll put my scale on this line. And some part will be here also. And I'll extend this backward. I will extend this backward. I'll extend this line only backward. This line I'll extend backward. So I take my scale and extend this line backward like this. See, here I'm not getting properly, but if you do know, trust me, you'll actually get a very nice diagram. Okay. Here I'm not getting it, but you'll get a very nice diagram. This is the way you have to follow. So you have to join the point of incidence to the focus first. In the case of a convex mirror, you have to join the focus and the point of incidence. Take your scale, put your scale on this line, okay, and then extend it backward like this. Here it doesn't appear to be good because actually, yes, I'm using free hand. That is why it is not appearing good. But if you do it, no, it will come very nice, okay? If you follow this process, okay? Now, I repeat, the reason we have put dotted lines here is because it is appearing to come from focus. I repeat, when the number of rays are coming parallel to the principal axis in the case of a convex mirror, they are going to diverge. You look here, a reflected ray is this one, reflected ray is this and this. Both are going like this. That means they are diverging. A reflected ray, if you see now, one is going like this, another is going like this. That means what? They are diverging only, right? They are diverging only, right? Yes or no? Now diverging, if you make it meet back, if you actually trace it backward, it will meet at one point, right? Yes. If the two rays are diverging, if you trace it backward, it will meet at one point, right? That is why we say it is appearing to come from focus, because it is meeting at focus, right? It is appearing to meet there, right? Yes or no? It is not actually meeting. See, if there are two roads, one road is going like this, another road is going like this, okay? There are two roads, one road is going like this, another, see, the two roads are going like this, right? See, they are actually never going to meet. But if you trace backward, they will appear to meet at one point, right? Yes or no, everyone? Same thing in the case of a convex mirror, they are actually meeting here. So we say that these two rays, that is this one and this one, they appear to diverge from the focus only. Okay. The reflected ray in the case of a convex mirror appear to diverge from focus. So here also, I have taken number of rays. Here I have taken 2 rays, but here we have 4 rays. All are coming parallel, and we just follow the laws of reflection. And you see that all the rays that are coming from focus only, right? Yes. And all the rays are diverging. Now, because in the case of a convex mirror, after reflection, the rays are going to diverge. That is why convex mirror is also called as a diverging mirror. Diverging mirror, okay? It is also called as a diverging mirror. Okay, you are putting R for repeat. Okay, now only I understand. Okay, now only I'm actually getting why are you putting R. Okay, okay. I thought he's actually putting R for angle of reflection earlier, actually. Okay. So Solon, you have to tell now. Like, I mean, I missed it. I thought it is angle of reflection you're putting every time. Okay, what do you want me to repeat? Tell me. What do you want me to repeat?
The diagram, sir.
Which diagram?
So this one, how the angle of reflection.
Okay, see. You have watched the first lecture thoroughly. First lecture you have watched. Did you attend first lecture on science?
Sir, yes, sir. But then you said that the most students do wrong, sir. What they do wrong. That one till there. From that.
No, you forget about what students will do wrong. You just learn the correct approach because you don't have to
No,
do
sir.
this.
After that, I didn't understand, sir. After that, I didn't understand.
Okay. I repeat quickly. Okay. See, first of all, what we are going to do is we are going to draw the incident ray. This is the incident ray. Yes or no? Maybe I'll actually make the line a bit thin. It will be easy for you. I have an incident ray here. Yes, this is the point of incidence, correct?
Yes, sir.
So actually what we are going to do is we are going to join this point to C. Why? So that we get normal, because normal is always through C in the case of a spherical mirrors. Now we have to also extend it backward so that we get normal here. This is the angle of incidence, the angle between the incident ray and the normal. This is a normal. This line is a normal, okay? So this is the angle of incidence. Are you till here understood?
Yes, sir.
So now, as per laws of reflection, I is equal to R. Correct?
Yes, sir.
So you just take your protractor, whatever is I, maybe it is 30, for example. So from this line, you measure 30 and you'll get this reflected ray. You'll get this reflected ray, okay? Okay, va? You'll get this reflected ray, okay, va? Yes or no?
Yes, sir.
So now, this is a reflected ray. Now, this reflected ray appears to come from focus. We know that, okay? It appears to come from focus. So what students will do is, first of all, they will draw this reflected ray, and then they will try to join to focus. And in that process, they will make some mistakes. I mean, they will actually randomly, see, they may also make the reflected ray like this, right? They may also, by mistake, they may also put it like this, and they will try to join like this. So line is not straight now. See, this line is like this line is like this. It is not straight, right?
Yes, sir.
Actually, it is a property of light that light always travels in a straight line. So this should be a straight line, basically. It's a straight one, right? This is a straight one. So that is why I'm telling you, before you draw the reflected ray, first of all join the point of incidence to the focus, because we know that the light rays is going to diverge from focus. It appears to diverge from focus. So you join that and then extend it using a scale. Same thing I've done below also. I mean, incident ray, this is a point of incidence. Normal is through C. So this is normal. This is angle of incidence. You take your protractor and mark whatever is I. If it's 30, this will also be 30. Reflected ray. Generally, students will draw the reflected ray first and then join. But I'm telling you, do the opposite. You join the point of incidence to focus and then extend it backward. You'll get the reflected ray easily. Punjacha.
Yes, sir.
Seri, okay. Perfect. And one more thing, everyone, please keep writing the notes on a regular basis. Otherwise, it will be very hard as we move forward. Very hard. Okay. So I is equal to R. This is loss of reflection. Okay. This is called a diverging mirror also. So principal focus of a convex mirror is a point on the principal axis from which beam of light rays initially parallel to the principal axis or the axis appears to diverge after reflected from the convex mirror. It's appearing to diverge only, right? Yes or no? Perfect. 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 Moving forward, we have a relationship between the radius of curvature and the focal length of a spherical mirror. What is focal length? The distance from pole to focus is focal length. See, suppose, maybe I'll actually. All of you tell me in the chat box, what type of mirror is this one? Concave or convex? This one. What type of mirror is this one? Concave or convex? All of you put in the chat box, what type of mirror is this? Concave or convex? See, it is concave. See, it's curved inward only. Just see, look carefully. I mean, it is curved inward only. Okay, it's concave mirror. Okay, even this is a concave mirror. Okay, both are concave only. Correct? Now, both concave and convex are part of a sphere. Now, just think about this. Okay, just think about this alone as of now. See, when I actually put it like this, okay, I have a concave mirror. I'm going to put it like this. So in 2D, I'll get something like this. Yes or no, everyone? I'll get something like this. Yes or no, everyone? Now, where is the reflecting surface? Inside. So non-reflecting surface is outside. I'll mark by hatch lines like this. Yes, this is actually hatch lines. I have tilted this one like this, and then I have drawn the concave mirror. Okay. Now I'm going to extend this, okay? I'm going to extend this, okay? Roughly. Then I'll get the sphere. Yes, then I'll get the sphere. Perfect one. You all of you try to use compass while drawing, okay? Then only you'll get perfect one. Okay. So now this sphere will have a center. That is called a center of curvature. Yes or no? Yes. Now, if this is a mirror, This mirror will have a center, that is actually center of the reflecting surface is actually called pole. And an imaginary straight line passing through both of them is actually called principal axis, PL, right? Principal axis, okay? So what is radius of curvature from pole to C? So radius of curvature is this one, okay? This is R, correct or not? Now, there is something called as aperture, okay? Aperture, okay? I'll just write the spelling first. We have something called as aperture, okay? A-P-E-R-T-U-R-A. All of you, please learn the spellings. If you don't know, write 10 times and practice. Don't be shy, okay? You do it. I have seen students committing spelling errors in 10th standard. You will not believe. I can show you. Actually, I have examples, okay? I have papers. Students commit spelling mistakes, okay? You should not do it. If you don't know, you practice. So what is aperture? See, if you have a look at this mirror, okay? If you have a look at this mirror, see, it is a bit curvy, yes or no? But overall, it looks a bit circular, right? Yes or no? Overall, it looks a bit circular, right? If you look at like the mirror, it looks a bit circular. If you look from far away, no, it looks to me like it's a circle. It's a circle. It looks to me like it's a circle. So circle will have a diameter. Yes. So this will have a diameter also. So diameter means from here to here, or you can measure from here to here or here to here, wherever you want, you can measure. It should actually pass through center basically. Okay. So suppose I take this one. Okay. So when you measure from here to here, no, diameter of the mirror or diameter of the reflecting surface. See, reflecting surface is a bit curvy, but if you see from far away, it's a bit circular, right? The reflecting surface is a bit circular, right? So the diameter of the reflecting surface is called as aperture. Now, what is radius of curvature then? See, radius of curvature, if you want to get, you have to first of all tilt the mirror like this. You have to draw the sphere. Okay, then you'll get radius of the curvature. So diameter will be, see, diameter of the sphere is this one. Diameter of the sphere is this one. Diameter of the reflecting surface is this one. Only this, see, generally in diagram, no, we mark the aperture like MN. MN means actually from here to here. It's actually here to here. So aperture is from here to here. Diameter of the mirror is from here to here. Are you all getting? Diameter means of diameter of the sphere, not mirror. I'm sorry. Diameter of the sphere is actually from here to here. Diameter of the mirror means only reflecting part. Diameter of the mirror, no, is actually from here to here. So this green color is called aperture. Yes, aperture is actually the diameter of the reflecting surface. Okay, I repeat, if you have this mirror, right? If you have this mirror, if you measure from here to here, okay, suppose this is center. See, this is a mirror. It's appearing circular, right? This mirror is appearing circular, right? That will have a center. Now, suppose you draw a straight line. Okay, suppose you draw straight line like this, through this only. So distance from here to here, no, this is called as aperture. Okay, aperture is the diameter of the reflecting part alone. Then what is diameter of the sphere? To get a sphere, see, this concave mirror would have been part of a sphere. This concave mirror would have been part of a sphere only, right? So how will we get the sphere? First of all, we have to tilt like this. You assume this mirror is tilted like this. Then you extend it. You will get the sphere. Diameter means what? From here to here. This is a diameter. See, we have not discussed diameter of the sphere. We have only radius of actually the radius of curvature. But diameter of the sphere is actually from here to here. Yes or no, everyone? So diameter of the sphere and diameter of reflecting surface both are different. Diameter of the sphere and diameter of reflecting surface both are different. Are you all able to understand that first? Yes or no? Both are different, totally different. Okay. So now, this is actually radius of, actually from here to here, if you measure, no, this is radius of curvature. This is radius of curvature. Okay. Okay, this is radius of curvature. So to get radius of curvature, first of all, you have to tilt. Then only you get radius of curvature. You have to draw the sphere and mark the radius. Okay. Now, I have given the definition of aperture, the diameter of the reflecting surface. Diameter of the reflecting surface, not diameter of the sphere. Reflecting surface. If you want to get sphere, you have to tilt and then you have to trace. Okay. Diameter of the reflecting surface of the spherical mirror is called aperture. Okay. Now, in our syllabus, we have mirrors whose aperture is very much small compared to the radius of curvature. Here, if you see now, it looks like aperture is this much, radius of curvature is this much. Actually, both looks to be same. Actually, it looks to both are same. But in reality, in our syllabus, aperture is very small, radius of curvature is larger than that. Okay, in our syllabus, we have only those spherical mirrors where aperture is much smaller than the radius of curvature. Okay, here it looks both are same, but actually in our syllabus, it's not the same. Okay, in our syllabus, the aperture will be smaller. That means green part will be smaller. Radius of curvature will actually be larger. Now, let me explain that in detail. Suppose, all of you look. See, actually here I have taken a picture. This is actually, I don't know, like this one. I don't know where I got this from. Anyway, it's okay. I mean, you can understand. See, this is actually, see, if this is center, right? If you measure from here to here, okay, this will be the aperture part. Yes or no, everyone? If you want to get the radius of curvature, you have to tilt like this. You have to place it like this, and then you have to extend. Mark center, radius of curvature will get. So, so actually, radius of curvature is this much part. Aperture is this much part. Aperture will see if you tilt. See if you tilt the mirror like this, diameter will be this part, right? Diameter of the reflecting surface. So this part is the aperture. This part is the radius of curvature. Are you all getting? Yes. So perfect, 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 perfect. Nice, nice, nice. Okay. Now, okay. All of you, before you answer any question, you have to first of all think, okay? I have taken a hollow sphere of glass and I have taken 4 different cutters. Red cutter, orange cutter, R for red, orange cutter, green cutter, yellow cutter, okay? All these are different cutters, okay? I have taken a hollow sphere of glass and I have taken 4 different cutters, okay? If I want to get a spherical mirror, please listen to the question. I mean, you have to think and answer. Don't randomly put any answer. It will not work out in the long run. Trust me. I have taken 4 different cutters, the same hollow sphere. If I want to get a spherical mirror with small aperture compared to the radius of curvature, I repeat, if I want to get a mirror with small aperture compared to the radius of curvature is this much, this like we measure like this, aperture we measure like this. If you want to get a mirror with small aperture compared to the radius of curvature, with which cutter should we cut the hollow sphere to make the mirror? All of you in the chat box. Very nice, Yogesh. Very nice. Okay, Somil, you are not right. Everybody else right. Very nice. Aryan, Suraj, Shauryan, Amurta, Naitik. Very nice. Thank you so much. See, I feel very much happy like when you people, I mean, answer correctly because I take so much of effort in explaining each and every concept. Okay, I give my entire energy. Okay, trust me, I give my entire energy. I mean, when you answer correctly, it feels very happy. I mean, I'm able to deliver. Well, I feel like, okay, I have like delivered whatever I wanted. Okay, Prisha, it is not right. Janav right, Srinika right, Asha right. Okay. Other people, please answer. Think and answer. No problem. I told if you want to get a mirror with small aperture as compared to the radius of curvature, which cutter will you use? Perfect, Mukesh. Very nice. Perfect, Somil. Perfect, Meenal. Sorry, yes, no, it's not right. Yes, Prisha, right. Let me discuss. All of you listen, okay? Maybe I can do it here also. Okay, maybe I'll take it here. Okay. See, when I cut using yellow cutter, okay, just focus on yellow cutter. I'll go from the right side. When I cut the when I cut the mirror using yellow cutter, I'll get only this much part. I'll get only this much part. Yes or no, everyone? Yes. So maybe I'll use yellow color and draw only this much. So actually I'll get this much part. Okay, I'll get this much part. Okay, I'll get only this much part. Now, if I want to get the sphere, what should I do? I have to actually, I mean, trace it like this. Okay. I'm sorry, sir. Actually, like if you look at the sphere, no, it's a bit bigger. I'm sorry. Just 1 minute. Okay. Just 1 minute. 1 minute. 1 minute. See, I'll try to explain here itself, okay? See, when you cut the, using yellow cutter, you'll get only this much part. You'll get only this much part. You'll get only this much part. Only this much part. When you try to extend the sphere, it'll be this much, this one. Yes or no? It'll be this one. Yes or no? Yes. When you cut that small part and when you try to extend, you'll get the sphere. Now that sphere will have a center. Yes. Yes. Now from center to pole, pole will be this one. From center to pole, this will be radius of curvature. Yes. What will be aperture? Aperture means from here to here only, right? Because if you cut this much part, reflecting surface will be this, diameter of the reflecting surface will be this one. So aperture is actually from here to here. Radius is this much. So aperture is small when we take yellow cutter. If you take red cutter, for example, you take red cutter, okay? Actually, it's like pink one, like looking like a pink one, it's okay. Okay, you take this much. So this much part, sorry. Okay, when you cut using this one, aperture will be bigger only, right? This is aperture. And radius of curvature appears to be the same, right? Both are equal, like appearing to the same, right? In our syllabus, we have spherical mirrors whose aperture is smaller, compared to the radius of curvature. So that is possible only using yellow cutter, right? Yes or no, everyone? Yes or no, everyone? Yes. If anybody wants me to repeat, you can actually always use capital R, okay? Use capital R hereafter. Okay. I hope everyone has understood, right? Good, 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 good. So now another concept. Just a minute. I think so. We are moving very slowly. I think so. Today ray diagram, I don't know whether I'll be able to complete ray diagram. It's okay. Next class, also everyone try to have those things. I mean, compass, ruler, and pencil. Okay. So now, all of you focus here. Okay. See, suppose I have a concave mirror, for example, something like this. Okay. Okay. So maybe this is a non-reflecting surface. Okay. And suppose I trace it to get the sphere, maybe I'll actually get a sphere like this, right? This is not from that hollow sphere. Randomly, I've actually taken from some other. Okay. Don't think it is actually from that. I have just taken it from somewhere else. So you think this is the hollow sphere. This is the center. So radius of curvature is actually from here to here. Yes or no? Yes. Now, I actually make the concave mirror something like this one. Okay, something like this one. See, this is more curvy, right? See, if you see this is a bit more curvy, right? Yes or no, everyone? It's a curvy, right? If you compare both of this is a curvy, this is a bit flat. Yes or no? Yes or no, everyone? Perfect. So now, if this is a non-reflecting surface, now if I extend this, okay? If I extend this, I'm extremely sorry for actually, it's like, I mean, cutting here also. It's like, you just, first of all, learn the concept, okay? So center will be somewhere here, pole will be somewhere here. So radius of curvature will be this one. See, when it is curvy, radius of curvature is smaller. When it becomes flat, radius of curvature increases. Yes or no, everyone? Yes or no, everyone? Now, if I make it a bit more flat, maybe something like this, a bit more flat, radius of curvature will increase. Yes or no? Yes or no? Radius of curvature will increase, right? Suppose I make it fully flat. Okay. Suppose I make a plane mirror, basically. Fully flat means it will become a plane mirror only, right? If I make it fully flat, it will become a plane mirror. It will not remain a spherical mirror. It will become a plane mirror. So suppose if I have a plane mirror, all of you please don't search the answer anywhere. Tell me what will be the radius of curvature of a plane mirror? Oh, Naitik has put, okay. Nobody is actually right as of now. Okay, no problem. Good. All of you have tried. That is actually the best part which I like. Okay, nobody's right so far. Okay. Okay. Srinika is very near. Very nice, Srinika. Good. Okay. Srinika, very good. At least you have thought in that way. Very nice. Actually, the word is not accurate, but you have actually thought in that angle. Very nice. Okay. Mukesh, you have given the right answer. Mukesh has given the exact right answer.
Sir, I
Okay.
have a doubt, sir.
Yeah, tell me.
Sir, plane mirror is not curved, sir. So can it have a radius of curvature?
So that is what I have asked.
Oh,
That is what I have asked, right? That is the question. What is the
sir.
radius of curvature of a plane mirror? Okay, let's all of you, let's understand. Stop writing. Okay. Very nice, Sanskriti. Good. Very nice. Good. Shaurya is very nice. You're right. Good. All of you listen. So we have 3 people who got it right. Shauryan, you're also right. All of you stop writing. Good. 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 All of you stop writing. All of you stop writing. Okay. See, when I take a very curved mirror, I'll easily get the sphere, and the radius is this one. Radius of curvature is this one. When I make it a bit more flat, you see the sphere is becoming very big. I mean, a bit big compared to this. Yes or no? When I make it flat, to get the sphere, right? If I make it flat, to get the sphere, I have to keep extending, keep extending, keep extending, keep extending, keep extending. It will never ever meet. We know, right? It will never ever meet. Actually, it will never ever meet. Okay. If you keep extending, keep extending also, it will never ever meet to give you a sphere. Yes or no? Yes. If you keep extending, it will never ever meet to give you a sphere. It will never ever meet. Now, you all have seen a railway track. Everybody has seen a railway track. We know railway tracks are parallel. We know that railway tracks are parallel. Now, suppose you are standing on the railway track. Suppose you are standing on the railway track here. And look at a very far away point. Look at a very far means infinity, okay? Very far means what? Infinity. Very far means what? Infinity. You look at a very far away point. It will appear to you that railway track is going to meet. Yes or no? Yes. When you're standing on the railway track, and if you look at a very far away point, it will feel to you that the railway track is going to converge at one point. It is going to meet, but actually it is not going to meet. It is never ever going to meet. It is just an illusion. It is not going to meet. We feel that it will meet. Same way, when the mirror is actually a flat like this, see when it is curved, see I told you, right? If I make it a bit more flat, after the radius will become the sphere will become very large and radius will increase. If I make it more flat, no, it will never ever meet. But we assume that if you keep extending, at infinity, it will meet. We actually like imagine like that. If you keep extending, it will meet at infinity. Okay. So that means you will get a sphere of infinite radius. Infinite. The radius will become very big. Okay. So radius of curvature of a plane mirror is infinite. Infinite, we use the symbol. This is actually infinity symbol. This is infinity symbol. So we say it is infinite or infinity. Are you all getting? Yes or no? Very nice. Very nice. Good. Good. I hope you're all enjoying. Okay. See, Ashley, I mean, you all know that actually I am not a school teacher. Okay, I really love teaching. Okay. And see, every year I have improved as a teacher. Okay. I always try to bring in some changes. I consider myself to be a lifelong learner. Okay. I always try to bring some improvement so that, I mean, it'll be easy for you people to understand. Okay. And you can always give some suggestions if you have, like, sir, like maybe this concept you can teach in this way. Maybe in our school they taught it this way. You can also give me suggestions. It'll help me improve so that next batches when I take, right, they will actually understand like maybe like much better. Okay. But still, whatever I'm delivering, I've actually referred to a lot of textbooks and then framed my class notes. So I tell my students that my class notes are enough if they actually listen properly in class and write the class notes within 24 hours and they revise before the class and come. Okay, that is what I tell my students. Okay, hopefully you'll also feel actually at the end Like maybe after 2 to 3 months, you'll actually feel, okay, when you appear for exams, school exams and all, you'll feel that. Okay. So radius of curvature of a plane mirror is infinity. Maybe I'll write that also because some students know they will not write that in the class notes. Okay. So radius of, they have asked this question actually in the exam. Okay. A radius of curvature of a plane mirror is infinity or infinite. Okay. Infinite is very large. Okay. Very large. Okay. So now I told you in our syllabus, okay, if you look here, no, look here, we are going to deal only with spherical mirrors with small aperture. Aperture is going to be small. Okay. We are going to deal only with small aperture compared to the radius of curvature. In our syllabus, we are going to deal with spherical mirrors whose aperture is small compared to radius. Aperture should be small compared to radius. Okay. Always. Okay. Now, why it should be like that? Because only if, remember this, okay, they will not ask this in the exam, but remember this, only when the radius of curvature is small, right? Sorry, only when the aperture is small, look here, only when the aperture is small compared to radius of curvature, focus will be a point. Okay, I repeat, when the aperture is small, see this is aperture, right, from here to here, and suppose this is radius, actually I'm getting a very big sphere. Okay, and maybe I'll actually draw the sphere to be very big one so that you understand the concept. Okay, this is aperture, center will be somewhere here, this is radius. See, the radius will be actually, maybe I'll use, this is maybe, this is radius. Okay, this is aperture. So aperture is smaller compared to radius. So when aperture is smaller, right, focus is actually a point. Otherwise, if you make the aperture big, no, focus will not be at a point. Focus maybe is like maybe over a region. I repeat, when you take the aperture to be bigger, no, focus will not be a point. Focus will be spread. That means when the light rays are coming, no, see, if I take a very big, like, I mean, aperture to be big, no, suppose I take this much aperture, okay. So when rays are coming, right, some rays may meet here also. I mean, some rays may meet here also. Some rays may meet here also. I mean, some rays actually, they will meet here. So focus will be spread. It will not be a point. If you want the focus to be a point, then you have to take small aperture, because then only the rays which are coming, no, they will hit only over a small region. And the reflected ray will always converge at one point. Are you all getting? Yes or no? So we take spherical mirrors with small aperture so that focus becomes a point. That is the reason, actual reason. But they will never ever ask. Okay. So now, when the aperture is small, right? When the aperture is small, focus becomes a point. Yes, and it has been found that focus is exactly the middle point of P and C. It has been found that focus is exactly the middle point of P and C. So now from P and C is focal length. Sorry, from P and F. From P to F is focal length. That means this will also become focal length because this is exactly middle, I told you. I repeat. Focus is exactly middle. Suppose I have a line. Okay. This is maybe P and this is C. Okay. This is 10 centimeter. Maybe, for example. So focus will be a like middle point, exactly the midpoint. Yes. So this will be 5. This will also be 5. So if this is F, this will also be F. This will also be F. So now from P to C is what? From P to C is what? From P to C is radius of curvature only, right? From pole to center of curvature is radius of curvature, yes or no? So can I say radius of curvature is F plus F, this F plus this F. Now this F is equal to this F because, see, this is actually not focal length, but this is becoming equal to F because focus is exactly middle point. Focal length is only this one. Focal length is from pole to focus only. But this is also F because F is exactly middle point. So whatever is this length, same will be this length. So R is equal to F plus F. So I can write R is equal to 2F. So radius is twice the focal length. This is applicable when the aperture is smaller compared to radius of curvature. There is a condition for this. This is not applicable every time. This is applicable only when aperture is smaller compared to radius of curvature. Are you all getting? Yes, I will write that maybe in the next page. Okay, just 1 minute here. I'll write some. Okay, just 1 minute, maybe. So relation, no? relation will be relation between, okay, just 1 minute. Maybe I'll actually put the, see, this is, I mean, aperture is not very small here. So maybe what I'll do now, I will redraw the diagram. Okay, I will redraw the diagram. So that will be easy for you to understand later on, okay? Somebody has asked some question. Okay. Somebody actually has put the relation itself in the chat. Okay, 1 minute. Okay, so I'll take, this is the aperture. Only this much, okay? This is looking very small only, okay? And actually I'm going to extend this. Okay? Okay? And concave mirror means I'll actually non-reflecting I'll mark. Okay? So from here to here, this is aperture part. This is aperture part. Yes. Aperture is smaller. Radius of curvature is bigger. Yes or no? Yes. So now why aperture should be smaller? Then only focus will actually be a point. Only when the aperture is small, right? Then only focus will be a point. Otherwise, focus will be spread. And for spherical mirrors with small aperture, focus is exactly the middle point of this one. Okay. It is exactly middle point. So if this is exactly the middle point, that means if this is F, this will also be F. Yes or no, everyone? Yes or no, everyone? So I can say R is equal to F plus F. That is R is equal to twice the focal. Radius of curvature is twice the focal length. Remember this. Very, very important and applicable only when I'll write maybe here itself. Applicable when the aperture is, maybe if I write, no, it will come to the next page actually. Maybe it's still I'll write. And when aperture is smaller compared to a radius of curvature. Applicable when aperture is smaller compared to radius of curvature. Clear, everyone? Very, very nice. Very nice. Okay. So now we have understood actually till here only we have seen. Next class, maybe we'll see the rules. See, rules are actually only 5 minutes. Okay. After 5 minutes, we'll start with the ray diagram. So I've taken ray diagrams actually drawn by some students earlier. So that will be easy for me. Okay. I will also teach you how to draw. Okay. Next class, I'll teach you how to draw all this. I'll teach you. So please everyone write class notes. I mean, I have taken this picture from class notes uploaded by one of my students actually in the previous batch. She was actually in 2023-24 batch. Okay. Her name is actually Mridula. She scored 96 actually in science. Okay. So all of you, please, I mean, keep writing class notes. Whatever I'm sharing, you keep writing. Okay. So that you don't have to, like, you don't have to write in one day itself. Okay. You keep writing regularly within 24 hours. Okay. So with this, we'll stop. If anybody is having a doubt, and one more thing before I stop, all of you, please join that WhatsApp community group. I have sent you a message, WhatsApp message a long back. I mean, I don't remember when I have sent you, but many of you have not joined. If I want to inform something, I will do it only there. So make sure that after the class is over, you join the WhatsApp community group if you have not joined, and the Google Classroom also, so that you can access the class notes. Okay, so with this, we'll stop. If anybody is having a doubt in whatever we have discussed so far, you can wait and ask. If you don't have a doubt, you can leave. Thank you so much, everyone, for joining in. Take care. Bye-bye, and have a great evening.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.